I cannot use this diagram as it is because it has lot of components in series and lot of components in parallel. So I have to simplify this diagram first before doing the mathematical calculations. Okay, so first simplification, we are going to use Miller's theorem. So R B dash C and C B dash C are between input and output. So I'm going to apply Miller's theorem and separate this components at the input side and at the output side. You know what is Miller's theorem? So Miller's theorem is used to decompose a component which is connected between input and output into two components purely at the input and purely at the output. So I'll be decomposing R B dash C and C B dash C using Miller's theorem. So you will parallel components at the input side, two parallel components at the output side. So see the next diagram. R B dash C by 1 minus A here and C B dash C into 1 minus A. So these two components you have here. At the other side you see C B dash C into A minus 1 by A, and I am neglecting the other value of RB dash C, which will be very high. So I am not considering RB dash C into A by A minus 1. So the value will be very, very less. So that our resistance is neglected in the output side. And I am additionally, you see, I am adding two capacitance C1 and C2. So it was not there, C1 and C2 was not there in the previous diagram, but see here I am adding C1 and C2, and C1 and C2 are the stray wiring capacitance in the input and output circuits respectively. So whenever you have a capacitor, definitely you will have a wire which will be coming out of the capacitor that is going to contribute to your capacitance. So the C1 and C2 I am adding externally, which will contribute to the stray capacitance at the input side and stray capacitance at the output side, C1 and C2. Okay, so now I have decomposed everything. So I have lot of components in parallel. So see, I have to make it simplified so that I can apply Kirchhoff's voltage law, Kirchhoff's current law, and write the equation for output voltage. Okay, and I'm assuming capital A is the gain of the amplifier. At the input side, you see I have three in parallel, right? C1. At the input side, you can see three capacitors in parallel: C1, CB dash E, and CB dash C into 1 minus A. So I can club them into a single capacitance CS. See here, I am clubbing them into a single capacitance CS. Whenever you know capacitance in series, I am going to add all the capacitance. So the input side, these three capacitance in parallel can be clubbed into a single capacitance CS. Same way in the output side, you can see you have again one more three capacitance in parallel. So C B dash C into A minus 1 by A, C2 and C dash. So I'm going to club these three capacitance and I'm going to write them as C. And these will be CS. Okay, I'm just combining the capacitance to simplify my diagram. So this capacitance CB dash C into A minus 1 by A, C2 and C dash. They are added and the equivalent values assigned to the capacitance value C. That's why I did not take C in the diagram. I took the value as C dash in the diagram because C will be the actual value of capacitance which will come in the formula for tuned amplifier. Okay, so input side and output side, 6 capacitance become 2. So these three will become 1 and these three will become 1. See here, same way. I am adding everything and I am equating it to C. So in this way, and also GCE is present at the output side. So GCE is actually 1 by RCE. Conductance is 1 by resistance. And if you write that in terms of H parameter, it is HOE minus GM into HRE. HRE is 0. So it is approximately equal to HOE. And HOE, you know, it is 1 by R naught. So instead of GCE, I'll be representing hereafter, GCE will be represented as R naught. 1 by R naught means it is coming in shunt. So that 1 by R naught will come, but the magnitude will be equal to R naught. So GCE is a very unknown term and I don't relate GCE to any of the circuit parameters. So I write GCE in terms of R naught. See, when GCE comes in series, it will be R naught. When GCE comes in shunt, to indicate that it is a conductance, I write it as 1 by R naught. And R naught is the output resistance of the current generator GMBB-E. Okay, and I have I in, you can see in the diagram we had this bypass capacitor CE, you had the coupling capacitor CE. So all these effect of CE and effect of CC are all negligibly very small, so I can neglect everything in the equivalent circuit. So two capacitors I have neglected, CE and CC. CE is called as bypass capacitor present at the emitter side, and CC is called as a coupling capacitor, which is used to couple the output voltage from one stage to second stage. So these two capacitances provide negligible impact on the operating frequency of the tuned amplifier.